All right, welcome back to the final week of, final lecture week of Introduction to Computer Networks. And hi, Vincent. All right. So let's see. We do have quizzes during this Saturday. Just like last week, it looks like there are lots of these quizzes you need to answer, but they are actually in just two series. Okay. Today we'll go through quiz 44, 45, and 46. And tomorrow, 47 to 50. And then, next week is the real final week. We will have the last exam, exam 3 on Wednesday, and there's not going to be a lecture on Tuesday. Okay, so you can use the time to study for the last exam. All right. And hi, Franklin and Chloe. Now, let's take a look at the topics today. Bad news travels slow and poison reverse. Okay, so as you can see here that we are not quite yet done with the routing algorithms. Okay, last week, if you recall, at the end I asked you guys to pick right between link state routing and distance vector routing, which one you would prefer. And hi, Mark. Hey, so many of you chose distance vector. You know what? And hi, Elaine. I think that's because we introduced both of the routing algorithms, but we only talk about the issues of the link state routing, right? So we kind of say that there might be an oscillation problem, right? If you don't set the metric to define the link cost properly. We said that we don't like the memory complexity, the space complexity, and the traffic complexity of link state routing. But have we talked about issues on the distance vector routing? We haven't, right? So the major topic that we'll be talking about is the issue of distance vector routing. So Polly will also take a poll again at the end of the lecture today, and let's see whether you will switch side. Okay. Now, distance vector. There is a weakness, a major weakness, in fact. Okay, so distance vector, let me just tell you ahead of time, doesn't deal with some of network changes well. Okay, so you see, changes of a network topology, some of those could be good changes. For example, link cost reduced from 4 to 1. Oh, okay, a lower cost, usually resulting in better, shorter paths, for example. Okay, lighter paths. Okay, so those are good news. In distance vector, good news actually travel fast. It's actually the bad news. So in case you have a link cost going from 4 to 60, okay, the cost certainly goes really high, then that is bad news. And in order for distance vector to finally converge to the stable, best new routes, it will take a long time. Okay, so good news travel fast, bad news travel slow. That is essentially what we'll be talking about today. Okay, so the first video is going to be introducing the issue and telling why good news travel fast. And to illustrate why bad news travels slow, we'll be going through quiz 44 to 46. It's an example in 3 phases. And you will see the point. You will see this characteristic of distance vector clearly. Bad news travels slow. So first video, about 2.5 minutes, you will see good news travel fast. So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converge really fast. But if it's bad news, meaning if a route suddenly go bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. So let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman forward. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1, so at time 0, y is going to detect the link cost change and update its dv and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore z is going to update the shortest distance to what? 1 plus the cost from going from y to x, which is 1 now, that is 2, which is better. Okay, so z is going to update its own dv and send it out to the neighbors. And y is going to receive z's update. Okay, z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I don't have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same. Okay, no more message being sent out, okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travels slow. So you see from the scenario, the link cost, instead of dropping to 1, now goes up to 60. Super bad news. Of course, x and y here will detect there's a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travels slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay. All right, so quiz 44. So this is the first phase of the bad news travel slow example. Okay, what you're seeing here is the same topology, except that we are changing from link cost 4 to 60. Okay. Do you see, if you recall, in distance vector algorithm, there are actually 3 steps in the infinite loop. First step is what? In case there's a link cost change or a connectivity change or a receiving distance vector from the neighboring routers, then we trigger step 2, calculation of the Bellman-4 equation. Now, in case the resulting vector after the Bellman-4 equation is different than the previous distance vector, then we propagate this new information to the neighbors, right? And those propagations of the distance vectors might trigger the neighboring routers to do what? Bellman-4 equation. All right. So what we are seeing here is what? A link cost change. So X here, observing a link cost change, needs to do what? To do the Bellman-4 equation calculation again. Similarly, X here, which is the other end of the link XY, will also see the link cost change and redo the Bellman-4 calculation. So for quiz 44, don't worry, Polly will show you, okay, how she calculates the new distance vector table for no X. And hopefully you observe and see if you can do the calculation for no Y. Okay, so here's the video, 2.5 minutes, Polly deriving X's table right after the change. And I call that moment T0. Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from the dx. Let me just show the final result real quick. The xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through 2 neighbors of x of the source, that would be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through the first neighbor y, what is the perspective? What is the shortest distance to the destination? Well,
y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy coming, came from no y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z. What is z's perspective, the shortest distance to y? That will be what? dz, to y. So dz to y. And that is in, distance vector of z came from no z earlier. Z to y, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
All right, so now your turn. Work on the table in no y at t0. So let's go to the score space, channel W15, quiz 44. This might be a little bit challenging because you need to recall the distance vector and the Bellman-Ford equation. So hope that you try to exercise this through, genuinely trying this through so that you don't have to study all that much, okay, for the last exam. So let me allow you 6 minutes time, so you do have time to think it through. Let's go. Guys, you might want to show the derivation. Okay, I think some of you might find that if you need to show the derivation, then hey, the answer come out differently. Okay, so this one is really tricky, guys. Okay, show the derivation, you'll see. Okay, by the way, real quick, sorry Pearl, sorry Vincent, it's not 5101. Okay, try again. I understand, because we can see the entire topology, right? As God, who know everything. Yeah, it is 5001. But you see, distance vector is not working that way. It's actually borrowing from the distance vectors from the neighbors. At this point in time, the neighbors have not yet updated their table. So you depend on the distance vector from the neighbors at the previous moment in time, which is before the change. Odd, isn't it? Okay, let's go on. You'll see. right, guys, you know what? It is 601. Okay, don't worry. Polly will show how she derives Y's table also in a 3-minute video. So in case you're, hey, confused, how come it's not 5101? Here's the video to look into.
dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is, hey, as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6, 6 wings. Okay, and that is actually going through no z. So y is going to pick, okay, saying to go to x. Let me send it to z first. And then z says, I know a way to x, which is, yeah, the O impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
All right, so now you've got the first taste of doing distance vector routing or working like a distance vector router. Now let's exercise more. So this is the second phase of the example for bad news travel. So next I'm asking you to derive the table at z, router z, after the first iteration at t1. So what is that? It's this. So we have already derived dx at t0, dy at t0. What does the distance vector algorithm do next? Yeah, so no x will send this to the neighbors. No y will send this to the neighbors. Right? So z here at t1, the next iteration will receive 0, 5150 and 601, which will facilitate the calculation of the new dz, right? Because after receiving vectors from neighbors, this router here, router z, will need to follow the Bellman-4 equation and get dz. Okay, and this is quiz 45, quiz 45. So let's go to the Discord space and channel W15, quiz 45. Okay, exercise again and derive dz. This time it should be easier, so you are allowed only 4 minutes time. Okay, let's go. right, I think you guys are getting it. All right, so now let's go on and move to, yeah, it is. It should be what? 710, right? So it will be like taking this route. So z is here. Z needs to find a way to x. So what is the best way? There are two ways, right? Going through y or going through x. Okay. If it goes through x, x actually tells you, okay, to go to x, it's best to go through either z or y. Oh, wait a minute. To go to z to go to x, there are two ways, x or y. Okay, and the better way, so this way is always big, right? 50. And this way, on the other end, going through y, okay, is what? The cos, link cos from z to y, 1. And the best way from y to x. And according to y, the best way to x is costing only 6. So 7. And how come y feels that the shortest path to x is only 6? Because y was told by z the best way is to go this way, 5. Okay, so you see it's odd. For a while, this is gonna be 710. Okay, so that actually takes us to the next quiz, quiz 46. This is the last phase of the bad news travel. So let's try to derive y's table at t2, which is here. We now know this is 7.1, right? What about this? At this point in time, dx came from x. dz came from z. So this is a new dz, therefore dy needs to be recomputed. Okay, so guys, go to W quiz 46 underscored. Okay, this one should also be relatively easy given how fast you guys finish quiz 45. So you have only 4 minutes to work on this one. And let's go and see if it gets really easy this time. Okay, I can see that you guys have got it. Yeah, it is a little bit weird because at any point in time, you are under the perception of the information you have collected so far. Okay, and when there's a change happening somewhere, it will take time for that information to gradually propagate. Okay, and there is a question from Mark saying, "What about if z doesn't receive both x and y vector, would it make sense to wait to receive at least two incoming vectors, assuming all edges go both directions?" So this is an interesting case. Okay, so in most of the calculations or even the problems that would appear in the exams, we kind of assume these vectors will arrive, okay, correctly. And there's not going to be loss of these distance vectors. But it could happen in practice that these distance vectors, as they are being sent, get lost somewhere. If that's the case, Mark, what's going to happen is that the router that does not receive new vectors will just stay quiet. They are waiting. They will wait because the algorithm says so. Does that make sense? Mm-hmm. Yeah. And that is going to slow down further how the system converge to the new shortest path. Okay. As we see now, 710 is, so this 7 here, so let me go here. This 7 here, okay, of course, is not the shortest path from z to x, right? Shortest path from z to x now should be just directly z to x 50. But it's under the perception that if I send it this way, it will be shorter because y used to know a way that's 6. And why does y knows a way to x is 6? Because z used to know there's a way to x that's 5. So 6, okay, if I send it to z, 1 plus 5, 6. So y then send it this way. And now z is saying that, okay, then I send to y knows a way that's 6, so together 7. And next is what? Y thought, okay, so the cost from z to x is now changed to 7. Therefore, the shortest path to x is through z, 1 plus 7, 8. Okay, and you can imagine what? This goes on and on. A01. If I ask you to calculate the z at t3, what would that be? Yeah, I think your intuition is right. But let me show you a video, okay? How poly derives dy at t2. And also, how come we need 44 iterations in order for this network to converge to the right, correct shortest path?
Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x. Through neighbor x, neighbor z. Link cost 60, link cost 1. Link cost 60, link cost 1. The xx, 0. The zx, look up the table. Z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only 7 dollars to go to x. And this is going to go on, in fact, because y here is going to announce dy also, okay, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, okay, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration, okay? And including the initial iteration, that will be what? 44 iteration, okay? Until, okay, Z discovered the true path. Next, then Y will discover the true path. And then everyone converge to the shortest paths that are really true.
All right, so in this scenario, you see that after 44 iterations, the system converged to the shortest path. There will be some scenario if a link cost is increased or the link is broken. That counting there, we see might count infinite amount of times, which means the system never converged to the shortest path. Okay, so that is the characteristic of a distance vector. I know. Now you might be swinging from distance vector being your favorite to link state a little bit. But wait until this. Okay, so this characteristic of distance vectors is actually not a good thing. Sometimes link cost does go bad. Okay, so Poisson reverse, okay, is a way to address this issue. Okay, the idea is quite straightforward.
The problem here is, okay, right after the link cost change, when Y is trying to recompute, okay, the best route to X to Z, okay, particularly to X. Bellman-Ford algorithm says Y needs to try, right, calculating the total cost through neighbor X, neighbor Z. Through neighbor X, best distance from X to X is 0, trivial, but the link cost is suddenly 60, okay, just to get from Y to X. So together, total cost 60. Okay, not very good. But the other neighbor here, Z, was still under the perception that the best route is this and the cost is 5. And Y here says the link cost between Y to Z is only 1. Okay, so Y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach X. Y does not know. Z is actually under the perception that this is the best route to go to X. So Z is going to send the packet back to Y. And Y is going to send it back to Z. Z is going to send it back to Y. So this packet here is going to loop for a while, okay, until Y discover, okay, the real shortest path to X. So Z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poisson reverse is working this way. This is to help, okay, preventing bad news travel slow. In Poisson reverse, Y and X, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite, okay. That way it prevents, okay, Y selecting Z, okay, as the shortest distance to X.
Okay, don't worry. It sounds a little bit abstract. Let me show you an example. Now, the example is a bit long, 5 minutes. But once you see the whole video, you'll see, okay, Poisson reverse is effective, okay, addressing this issue of, temporarily under the misperception of a previous better route.
Let's use the same example to illustrate how Poisson reverse works. So taking one step back, before we have the link cost change. Now Z here will discover a shortest path to X this way, Z, Y, X. So shortest distance from Z to X is 5. And the next hop router is Y. Now, link XY here, the cost changes from 4 to 60. X, Y, these two routers being connected to the link will be able to discover the link cost change. But Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay? A funny value for the shortest distance from Y to X, which we see from the network after link cost change. There's no way this is the right value. So to avoid having confusion such as this, we should stop z from keep telling y this is the shortest distance. So z tells y instead, the distance to x is not 5, instead being infinite. And that is what you're seeing here. Distance from z to x at y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. If this node here discover there's a route coming from the neighbor and using itself as the next hop. So if y here discover in one of the neighbor, and this neighbor is using itself as the next hop to a destination, set this entry here in y's table to infinite. With now dzx being changed to infinite, the way we calculate dy in iteration t0 will be different. So dyx particularly is the entry with different value. It was previously 6. But now let's see how it's going to look like from y to x. There are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx, dxx, dzx. Set up table, xx, 0, zx, infinite. So 0 here, infinite here. Comparing the two, 60 better. Therefore, shortest distance from y to x is now, the direct link xy. And then, the next point in time in t1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. dxx and dyx, dxx, dyx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. And so y here, recalculating dy again, the dyx is going to be different as well. So dyx. Two neighboring nodes, 60 and 1 are the link cost. dxx, 0, dzx, zx, entry value being 50. So 51 compared to 60, 51 wings. So to go from y to x, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
Alright, so you see Poisson reverse works. So the idea is essentially to avoid those previous paths that to avoid those paths that paths that involve the link that is experiencing a change. And we have one more video to close the routing algorithms, and that is about 5 minutes, and we only have 2 minutes left till the end of the class. So what I'm going to do is a poll. Now, think again. Would you prefer link state or distance vector routing now? So type up your choice, DV or LS. And with that done, then that's all we have today. And tomorrow is going to be our last lecture. Hopefully we'll be able to summarize the 2 routing algorithms and talk about internet routing, how we use these two algorithms, and where we use these two algorithms. We actually use both of them. Oh, okay. Hey, interesting. Interesting. Okay, so I see there are more link state supporters definitely this time. Okay, but some of you still prefer distance vector. Might be because this bad news travel slow issue had a remedy. Like if we implement Poisson reverse, then yeah, it might not be so bad. Okay, so DV, yeah, but slightly more link state, I guess. Yeah. Okay. Good. So that's all. Bye. I see you tomorrow. Okay. Oh, music. Okay, bye.